In section 4.5, we're going to be graphing rational functions. So we'll start with the definition. A rational function is a quotient of two polynomials, p of x over q of x, where q of x can't be zero. And so we start with finding the domain of these rational functions on the left. Notice that I went ahead and factored them on the right side there so that we can easily identify the restrictions on the domain. Now in the first two equations, rational equations, here's one, two, actually these are rational functions. In the first two, we can see that x is in the denominator, so x can't be zero. In the third one, in its factored form, we can see x can't be -2 or 1. In the fourth function, x can't be 3. In the fifth one, x can't be -1 or 2. And in the sixth one, x can't be -1. Now your homework might ask you to write it in interval notation, so you have some examples here. So know that when we're graphing rational equations, the domain is important because it tells us where the graph has some discontinuities, which are breaks in the graphs. So in example 1, we're going to find the domain, f of x equals 1 over x minus 3. I have it sketched here to the left. And if you take the denominator, x minus 3, set it equal to 0, and solve for x, we can see the domain can't be, x cannot be 3. And I wrote it in interval notation. So we could also look at on the graph, that the graph is never crosses this line, this vertical line here at x equals 3. Forgive my drawing a little bit, but the graph should not be crossing that line. We call this a vertical asymptote. It has something to do with the zeros of the denominator. So a vertical asymptote, where the rational function has no common factors in the numerator and denominator, they will occur at any x value that makes the denominator equal to 0. So if a is a 0 of the denominator, then x equals a would be the vertical asymptote. So for example, number 2, determine the vertical asymptotes of the function. If we factor the denominator, we'll have x plus 4 times x minus 2. So x equals -4 and x equals 2 would be my vertical asymptotes. And if you were to sketch that, you would look for 1, 2, 3, 4. There's my x equals -4. And then at 2, we could put a dotted line through x equals 2. And so those are the asymptotes, those are the vertical asymptotes, and it's where the graph will never cross those lines. On example 3, I have a sketch of this one. Find the vertical asymptotes of this graph. G of x equals x cubed divided by 4x cubed minus x squared minus 68x. So the first thing we do is factor, and we have x cubed divided by x over 4x squared minus x minus 68. So it may not be as easy to factor that quadratic. So to help us, let's use our graph. So I kind of copy and pasted it over here, and I'm seeing that -4 might be a vertical asymptote on this graph. That's what it appears like. There's a couple ways to check. You can either go to your table of values, and in which case, if you have an x of -4, your y may say error, which means that the graph does not cross that point. So that's one way to check. Another way to check is to actually plug it into the denominator and see if that forces it to be equal to 0. Now, I prefer this method because this is going to help me find, actually, we don't have to check it if we use a table, but we do need to check it some way and then use it to find the other 0. All right, so plugging that in, we indeed get 0. Therefore, x equals -4 is the left asymptote. So to find the other 0, I can use synthetic division. So the 4x squared minus x minus 68, I'm just going to look at the coefficients. And we're going to divide by -4, which we know is a 0. Bring down the 4, multiply. 4 times -4 is -16. Add, and we get -17. Multiply by -4, and we get positive 68. Add, and we have a remainder of 0. And so what's left is 4x minus 17. Set it equal to 0 and solve for x. And so we have x equals 17 over 4. And so that's my other 0. And so we just found our other vertical asymptote. So our two vertical asymptotes are x equals -4 and x equals 17 over 4. So we can see over here on the right side, even though it was close to 4, it wasn't really quite exact. But now we know this is x equals 17 over 4. And you can double check in your table when you graph this. If you put in 17 over 4, you should get an error. So note this, that if you set the table in ask mode and you can enter the asymptote numbers, you'll be able to get those fractional numbers or decimals. And the output will result in an error if it's a 0. And that's because the graph will never cross that asymptote. Now we can also find horizontal asymptotes, and that's when the y values are approaching some real number b, excuse me, as x approaches either infinity or negative infinity. So the way to find a horizontal asymptote is to compare the degree of the numerator and the denominator. So if the degree of the numerator is less than the degree of the denominator, then y equals 0 is going to be your horizontal asymptote. Okay, and a lot of times we say the degree of the numerator may be like n, okay, and the degree of the denominator is m. So if n is less than m, then our horizontal asymptote is y equals 0. In another case, when the numerator and denominator have the same degree, that is n equals m, then the horizontal asymptote will be the coefficient of the lead terms. So if a is the lead coefficient of the numerator and b is the lead coefficient of the denominator, then our asymptote is y equals a over b. Then when the degree of the numerator is greater than the degree of the denominator, we do not have a horizontal asymptote, okay? We will actually get an oblique asymptote instead, which an oblique is a slant asymptote. So in that case, when you get a slant asymptote, that is when the degree of the numerator is greater than the denominator, you're going to divide the polynomial in the numerator by the polynomial in the denominator, and and that will get you your, this is to get the quotient. And the quotient will be your oblique asymptote, and it'll be a slant asymptote. Let's say, okay, so in example 4, find the horizontal asymptote. Let's see, we've got the degree in the first, in the numerator is 1. All right, so n is 1, and m is 3. That's the degree in the denominator. Since n is less than m, then our horizontal asymptote is y equals 0. In example 5, we can see the degree of n is 2, the degree of m is also 2, and since the degrees are equal, the horizontal asymptote is a over b. A is the coefficient of the highest term, which is 2. B is the coefficient of highest term in the denominator, which is 1. So y equals 2 is going to be our horizontal asymptote. And then to graph this, I went ahead and put it on our T84, but we could also find some other ordered pairs. So I'm going to go ahead and draw the horizontal asymptote. And that's going through y equals 2. And so we always draw the horizontal and vertical asymptotes as dotted lines. So this is the line y equals 2. Now we see also that there is a vertical asymptote through x equals 0, because remember that's the zeros of the denominator. So x equals 0. And so the question is where to draw the graph. Again, you can use your calculator to really aid in this process. If you didn't have your calculator, you can just find some ordered pairs on either side of the 0. So I chose a couple, some easy ones to calculate, f of 1 and then f of -1. When you plug those into your original equation, we get f of 1 equals 3, f of -1 equals also 3. Okay, so it's f of 1 is 3, so that's about right here and right here. And we already know then that the line or the graph will have to go through that point and will hug that line and get awfully close to y equals 2. Okay, but plotting those 2 points told me that I was definitely going to have my graph in quadrant 1 and quadrant 2.